At this point, we are going to hear from Dr. Juan Lorenzo, who has, I know this conference has been going on or symposium for 3 years, and I know that Dr. Lorenzo was with us last year, and he's graciously come again. He grew up in Australia, did his undergraduate work in Spain, and did his graduate work here in the United States. And he is a seismic expert. I know that's not a scientific term, but last year, I know his presentation focused on seismic issues. He does a lot of research in the geophysical and geological realms, and this year is joined by Jason Hicks, who is helping him with one of his projects. Jason, if you could stand for a second. This is our next generation of geologists, so thank you. And if you have any questions that Dr. Lorenzo can't answer, I know Jason can. So
yes. He's
working at LSU in geophysics. He's getting his master's in geophysics, if I understand correctly. And so he's working on this project by a National Science Foundation grant that's helping with some of the costs of this project. But Dr. Lorenzo is going to be our first presenter in the second half of our presentation. So Dr. Lorenzo, if you'd help me welcome Juan Lorenzo.
Thanks very much to the New Orleans Geological Society and all the other surveys and all the hard work of the many people that have put this symposium together. Every year it seems to get bigger and better. I'd like to thank Mike Merritt for all his hard work, and I apologize if I've forgotten any individual people's names. Next slide, please. This is work that Jason Hicks, as part of his master's program at LSU, is doing, and that he's helping me do in the field. Generally, we know that levees, or artificial embankments, or levees as we call them locally, can fail for many different reasons. Some of the easier reasons, or simpler reasons to understand, are erosion caused by currents flowing over the top or beside the levee, and that can lead to artificial embankment, or I'm going to say from now on just levee failure. Next one, please. So as these currents overtop the levee or cut the underside, they can erode and eventually destabilize the levee and lead to total failure. But there are other mechanisms that we're all more than keenly aware of that can lead to levee failure. Next one, please. There are more deep-seated causes for levee failure that we don't see immediately at the surface of the land. Some of them may be in the less than desirable engineering materials that we use in the levee. And I've tried to represent those less than desirable materials by those little brown infilled rectangles on the right there. They might represent just materials that the contractor decided to put in while he wasn't being supervised. Now, and this happens all over the world. It has nothing to do with Louisiana, it's just human. The white arrows may represent seepage, or water coming from the protected side, in this case on your left, percolating through the sediments and coming up the other side. And if they pipe or entrain any of the materials, they could severely destabilize the overlying levee body. There are even deeper causes, such as just the naturally extremely weak soils that we have here in Louisiana. And the deeper hidden reasons for levee failure, or potential levee failure, are really suitable to geophysical techniques. Geophysical techniques are non-invasive, they don't damage the levee, you can conduct them on the surface, and they're relatively cheap. They have some drawbacks because they're going to give you a general overview, but just as they find oil and gas, in conjunction with point studies, with well logs, geotechnical borehole logs, the marriage of these two types of technologies can potentially provide very important and useful information for monitoring and managing our levee system. Next one, please. To start this off, we have a really good natural laboratory of a levee that's actually experiencing failure as we speak. And it's a perfect place to go see if we can find the reason for these large fissures. The area and study I'm referring to is located on the west bank within the confines of this yellow rectangle, just a few miles south of Marrero and a few miles to the west of the Mississippi River. Next slide, please. As you can see, the cracks in the levee are large enough. I'm no giant by all means, but you can see that I could be swallowed up to my knees inside these cracks. So these cracks are probably 1 to 2 feet wide, and they can go on for at least 200 or 300 feet along the levee crest themselves. So this is a perfect place to see if we could understand, come up with a predictive model, a tool, invent a tool that could locate the causes, potential causes for this damage that we see at the surface but at depth. Next one, please. Okay. This is a picture of the levee crest that's damaged looking to the south. So those big trees on the left are on the Mississippi River side. That would be the unprotected levee side. And the water that you see in the distance on the right, that's where the sediment was borrowed to build up this crest. And the little marker in the middle, that's for reference, that's one of the markers that they have along the levee, so it lets you know where you are. And I don't know if you look carefully in the foreground, you might see a slight dip and like a slight little cliff along the crest of the levee, and I've interpreted in the next slide for you. So that's where I've interpreted the fissure to be, and it's not straight, it's not caused by pure tension, but it's curvilinear, it's arc-shaped. And when you have arc-shaped fractures of this type in geology, the most classically held understanding is that it's caused by lateral movement, by some small degree of slumping or shifting of the materials away from the crest and down. So there's some movement of the material to the side. And the prediction of this type of interpretation is that there should also be a bulge somewhere at the bottom of the levee where the material lays to rest. So if this is the valid idea, we should be looking for this bulge to support this idea. This is more or less what the fissures look like. Next. And in an aerial photograph, it's kind of a trick aerial photograph, the colors represent the elevation of the land, and they're collected by a technique similar to radar, where you use the invisible light spectrum to bounce light off the surface of the earth, and depending on how long it takes to come back to the plane, you can tell what the relative elevations are on the surface of the earth. Well, the levee lies underneath those white rectangles and those white diamond shapes. Those white rectangles and the two diamond shapes represent 5 places where we conducted some seismic tests in order to understand the physical properties or the strength of the materials at depth. And the orange circle behind them all, that's the bullseye where most of the fissures were located along the levee. The dark purple area, that's the land surface that from the scale at the bottom you can see is around anywhere from 0 to 5 feet below sea level. That land surface was really at sea level, before the levees were built in the 90s, but has since subsided down to those elevations of about 5 feet below sea level. We did 2 different types of seismic experiments, and I will explain in the next couple of slides what seismics really is. But there are 2 different types, and I pinpointed them with the diamonds. The diamonds represent seismic experiments that are very similar to medical CAT scans. I would call them seismic tomography. And they were carried out just to examine the conditions of the levee itself near the crest, to get a good reference on what those materials were like. But the other 3 rectangular areas were experiments done on the berm, on the side of the levee, away from the crest, on the flat part, on the protected side. And there we use very conventional types of seismics. And seismics have been used for 40 or 50 years. They're very standard. Billions of dollars have been invested in this type of technology, so I'm not reinventing the wheel. I'm applying it and inventing a new application for this proven technology.